Welcome to the fifth and last session of the energy storage module. We will hear today about storage technologies for long-term storage, hydrogen and its derived fuels, heat storage, why are technologies more suitable for long-term storage. To go back to the energy storage densities for different systems, we can see interesting high energy density options here. The energy densities of compressed hydrogen, synthetic natural gas, liquid ammonia or artificial oils are indicated, and one can see they are ranging in size. These indicated fuels can be produced from renewable hydrogen and, for instance, nitrogen from air or carbon dioxide from a sustainable source. Then these fuels can be used for long-term storage. For the indicated fuels, we already know how they can be stored in suitable ways. Hydrogen and derived fuel examples. These artificial fuels can be produced from renewable hydrogen and nitrogen or carbon dioxide, as we also saw in the storage session 2, for making the industrial energy use renewable. Apart from these thermochemical routes, also electrochemical routes are being researched. Here, a basic electrochemical cell is shown in which at the negative electrode hydrogen is produced from H2O, and at the positive electrode oxygen is produced. The OH- that is produced at the negative electrode travels to the positive electrode. It is called alkaline electrolysis because the electrolyte is an alkaline solution. The overall reaction is water being split into hydrogen and oxygen. There is a membrane separating the hydrogen and the oxygen. On the picture, one sees an alkaline electrolyzer stack that has many cells of the previous slides in series. Some general alkaline electrolysis characteristics are listed here. That's used at scales from megawatts up to several hundreds of megawatts. It's considered to be the lowest cost electrolysis. It can use nickel-based electrodes and potassium hydroxide in water as an electrolyte. It's very durable when running constantly. Single cells are stacked in series, and the technique still actually needs to learn how to work with intermittency. The energy efficiency can be 65 to 80%, depending on the current density that is used. And these electrolyzers are run at high currents normally to make the best use of the installation, and that results in efficiencies that are lower than when one would use them at lower currents. This is a picture of a large-scale alkaline electrolyzer as it was used until 1991 in Norway. Now, new gigawatts electrolyzer designs are being developed to enable large-scale hydrogen production from renewable electricity. Here one observes the electrolyzer stacks with gas collection equipment and also compressors in the back. On the image, one also sees the high voltage power electronics as part of the plant. Another type of electrolyzer is a polymer electrolyte membrane electrolyzer. In the animation, you see how it works. The electrochemistry has the indicated half reactions with at the negative electrode, the cathode, protons and electrons forming hydrogen, and at the positive electrode, the anode, oxygen and protons and electrons are produced from water. This all takes place in an acidic environment where the solid acidic electrolyte takes care of the proton conduction. Because of the acidity, one can only work with noble metal, platinum and iridium-based catalysts. The membrane also separates the gases. When using PEM electrolyzers as storage means for intermittent electricity, still some further developments are required. It is considered more costly than alkaline electrolyzers, and the energy efficiency ranges from 65 to 75%, depending on how much current is fed to the system. In Delft, we developed an integrated battery and electrolyzer on the basis of an alkaline nickel-iron battery. The basic notion is that in a renewables-based energy system, one requires large-scale short-term storage in batteries next to long-term fuel storage coming from hydrogen out of water electrolysis. This integrated battery and electrolyzer has both aspects with only one set of materials for the electrodes and the systems around it, such as the power electronics and the balance of plant. So that provides a material saving. Also, it makes that using lower currents does not only increase the number of cells, but it makes the battery capacity and the energy efficiencies higher. Inside the cell, it looks very much like an alkaline electrolyzer. The difference is though that it are now battery-type electrodes that are charged first with the indicated electrochemical reactions involving iron and nickel-based materials. When the electrodes are fully charged, the iron and the nickel hydroxide that are formed act as the catalysts that split water in hydrogen and oxygen. When there is a lack of electricity, the battery electrodes can be discharged to provide electricity. So this can work with intermittent renewable electricity at one moment as a battery and another moment as an electrolyzer. And it uses no noble metal catalysts. Let us now look to a whole energy system then. The renewable electricity from the grids will be coming from intermittent sources. When there is too much electricity, it can be stored in batteries, and when they are full, converted to hydrogen. Here, ammonia is used as example for hydrogen storage because this molecule does not need a carbon source and it can be stored as a liquid. When there is too little electricity, first batteries can be discharged, and when they are empty, the stored fuel can be used in gas turbine power plants to produce electricity. The conversion of ammonia to hydrogen, or cracking, may be done before that. The hydrogen is also used as industrial feedstock. In this way, both the electricity supply may be stabilized on short and long timescales, and also the chemical feedstock supply can be stabilized. Sustainable ammonia, NH3, as large-scale hydrogen storage, what is that good for? Well, let's look at this list of characteristics. It can be produced from green hydrogen and nitrogen in air. Air is 78% nitrogen, so it's easy to obtain. Much easier than, for instance, carbon dioxide with its low concentration in air. Ammonia manufacturing uses iron as a catalyst and as pressure containers. That is not an expensive material. Today there are storage containers of liquid ammonia of 100,000 tons. With its high energy density, that means such 100,000 tons container contains 625 gigawatt hours. One can therefore envisage terawatt hours of storage on industrial sites. Ammonia itself can be used as a fuel in a gas turbine for electricity generation. Next to that, it is also an agricultural fertilizer and chemical feedstock and hydrogen storage. An important remark, though, is that ammonia itself is poisonous, so it needs to be handled with great care. However, there's 100 plus years of industrial know-how on an operational scale that is already very large. The current energy use for ammonia production is about 1.5% of the world's energy use. In case of a spill, it is biodegradable as it is a fertilizer. That is different for instance, methanol, which is equally poisonous and can reduce plant growth. When large-scale storage is enabled, industry could operate as illustrated here. When using batteries and electrolyzers plus the feedstock storage, one can envision that industry can run continuously on the stabilized flow of electricity and feedstock. In this graph, system sizes for storage of fuels can become very large as shown. Power to gas indicates power to gas here. So electricity converted to a fuel like hydrogen or synthetic natural gas. PTL is power to a liquid fuel. Note that storing on these different scales lead to different total energy volumes. The batteries are going towards multiple gigawatt-hour scales for one site. They will be cycled many times a year to the electricity, so the electricity throughput can be hundreds of times higher. The fuels go to larger unit sizes because they are cycled only maybe once a year. Obviously, the system is very much under development. The previous slide also includes thermal storage. An important example is the air conditioning in buildings, which is cooled in summer by cold water from underground layers. The resulting heated water is stored in the underground for use in winter, when in winter the still warm water is used to heat the buildings again. So that is seasonal energy storage. Why are fuels more suitable for long-term storage, one may ask? The energy efficiency for electricity storage using fuels is unfortunately not very high. It is the product of generating the fuel, storing it, and converting it back to electricity. Roughly 40% can be reached. Although this efficiency is low compared to batteries, it has the advantage that the fuel molecules can be stored relatively cheaply and at the required very large scales. Batteries are only economical to a size that they can often be cycled on a short time scale. In addition, the long-term storage enables electrification because it guarantees security of supply at times of low renewables and when the limited scale batteries are empty. So whatever society does, it needs security of supply, which means long-term storage backup power for when the sun and wind have too limited output. This concludes the Energy Storage Technologies module. Thank you.